Okay, so some definitions here. Discrete random variables, what does that mean? So in experiments, data is often collected in numerical form. For instance, 3 coins are tossed and the number of heads showing is recorded. You say the number of heads is a random variable that has the because it's random. There's no way you can change it or predict what's going to happen. So it has possible values. When you toss those 3 coins, you might have 0 heads, you might have 1, you might have 2, or you might have 3. There's 3 coins. When you're talking about the number of heads, then there's 4 possible. Okay, so another example of a random variable is the volume of water in a 50-liter ring barrel, which has the possible values. Well, the values are anywhere between 0 and 50 milliliters. So you could say, if we call it x, then x is less than or equal to 50, greater than or equal to 0. Okay? Think about that. The amount of rain, you could have decimal values, fraction values, etc. Right? So you could have, if you had a good enough measuring tool, you could have 42.1376 milliliters. So you can have any value between 0 and 50. With the number of heads, you can't have part of a head, right? You can have 0 heads, 1 head, 2 heads, 3 heads. You cannot have 1.32 heads. It's just not possible. So we're going to split this up into discrete and continuous. So definition, a random variable x represents in number form the possible outcomes that could occur for some random experiment. When x equals the number of heads showing, it has those values, 0, 1, 2, 3. You say the number of heads showing is a discrete random variable because its possible outcomes are a subset of the whole numbers. A discrete random variable x has possible whole numbers, lowercase x, where x is an element of the set of whole numbers. So in IB, we use n for that. Okay. In Alberta education, n is natural numbers. A continuous random variable x has possible real number values in some interval. So it's got a range of real values between 2 boundaries. So the volume of water in a 50-liter rain barrel is an example of a continuous random variable. Here's a couple more examples. If x is the quantity of fat in a T-bone steak, then x is what kind of variable? So can you have 0.34 milliliters of fat in a T-bone steak, a decimal value? Yes. Okay. Number of hairs on your cat. A hair is a hair, whether it's short or long. So that is discrete. Okay. So you can't, even if it's a short hair compared to a long one, it's still one. Think about it as hair follicle, maybe. In any case, so this is discrete, and this is continuous. Same words we use for functions, right? We were talking about domain and range. So, some possible probability distributions. How can we display the data? So for a discrete random variable, we can give it in a table. We can graph it with a probability spike graph or distribution histogram, or a function form, a probability function. Okay. So we'll do some of that in a sec. Here's some examples. Consider the experiment of tossing a coin 3 times. So like we talked about before, list all the possible outcomes. So if you want to do a tree diagram, you can. So you would have heads or tails to start. From there, heads or tails. And then from each of those, heads or tails. We did that the other day, right? So the possibles are 3 heads, 2 heads and a tail, heads, tail, heads, heads, tail, 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 heads, I just wrote them out from my tree diagram. So what's your random variable? So it says let x be the number of heads observed in each case. List the possible values of x and find the probability of each value. So remember the 4 possible values: no heads, no heads, 1, 2, or 3. So what's the probability of getting no heads? So that would be only this one. So 1 out of 8. 1 head would be 1, 2, 3 out of 8. And 2 heads, that's going to be 1, 2, 3 out of 8. And then 3 heads is 1 out of 8 as well. So explain why this random variable is considered discrete. As I said before, you can't toss part of a head. All right, so complete the following probability distribution table. All right, so for this is already entered. For 1 head, it was 3/8. For 2, it was 3/8. For 3, it was 1/8. Okay. Remember that probabilities cannot be less than 0 or greater than 1. So for each probability, so these lowercase p are each of these probabilities, the value has to be between 0 and 1. Okay. And the sum of all the probabilities has to equal 1. So if you take a look here, they all have a common denominator of 8. If you add the numerators, 1 plus 3 plus 3 plus 1 is 8. So that equals 1. All right, in any probability distribution function, P is the probability of an event, then P is between 0 and 1, so that's just summarizing it. The sum of all the probabilities in a distribution table is 1, so if we use summation notation, that's equal to 1. It's just restating it, okay? It's going to be a discrete random, or just a random probability experiment. The probabilities have to add to 1, whether it's discrete or continuous. Okay, so now we're going to, for that data, draw a probability distribution spike graph and a histogram. So label them with your, these are going to be your discrete data here. So this is the number of heads. So 0, 1, 2, 3. So even though we often put 0 on the vertical axis, in this case I'm going to actually put it away from the vertical axis. It's not wrong if you put it on the vertical axis, right? Because that kind of makes sense, but we're going to put it away just to make it easier to distinguish our spikes. And then here, this is going to be, because it's probability, probability. It's not saying, okay, I'm just going to write it horizontally.
the shadow is not letting. Oops, that didn't spell it right either. Okay. So, vertical scale. So we have values of 1/8, 3/8, 3/8, and 1/8. So the smallest is 1/8, the biggest is 3/8. So take a look. We've already done some scale markings for you. I would make each one 1/8. And 2/8 is really 1/4. But that makes it equally spaced. You always have to do that. And then for 0, it goes to 1/8. So a probability spike graph, use a ruler. I'm just going to use my straight line just to, my smartboard is finicky. Okay, so they look like spikes. And here, because it's a histogram is like a bar graph, we're going to label in between. So 0, 1, 2, 3. And then probabilities are still, so actually I'll use 1/4 and then 3/8. And then do your bars. Okay, so example 2, explain why each of the following are not probability distributions. So gives you a hint, they're not. So you have to think about what reason it would be. So this one, the actual values, data values, are the same as that tossing the coins, 0, 1, 2, 3. Take a look at the probabilities. So 0.4, 0.6, 0.3, 0.1. If you add those together, you get more than 1. Okay? And so the property is that in an experiment, the probabilities have to add to 1. Not more than 1, not less than 1. So here, so if we add these, we get what? 1.4, which is greater than 1. So since the total of the probabilities is greater than 1, it is not a probability distribution. Next one, you're going to have to calculate each probability. So there's a formula there. So when P, where X equals 0, what's that going to be? That's going to be 1/2. 0 plus 2 is 2. The probability where X equals 1 is going to be 1/3. Right? You put 1 in for X. The probability of X equals 2 is 1/4. The probability of X equals 3 is 1/5. Okay. Common denominator, what's 60? So that's going to be 30 over 60, 20 over 60, 15 over 60. So right away, once I get there, I see that the total already is greater than 1, because that's going to be 65 over 60. 12 over 60. So total is greater than 1. So same reason as the first one. So not probability distribution. And then this one is a graph. Take a look. It's got a negative probability. Can't have a negative, right? So that probability is less than 0, therefore not a probability distribution. All right, then example 3 says determine K for the probability distribution, where the X values are 1, 2, and 3, and then find the probability of 3. So our property is, for a probability distribution, is the total has to add to 1 of all the probabilities. Okay, so when P of 1, that's going to be K times 1 plus 2, which is 3. I'll just put that in right away. P of 2 will be K times 4. P of 3 will be K times 5. Okay. So, therefore, 3K plus 4K plus 5K has to equal 1. Well, K equals 1, K equals 1/12. Okay. So now the probability of 3, remember it's equal to K times 5. So K is 1/12 times 5 will be 5/12. If you continue on and take HL, you will, once you learn intervals, then you go back to probability in HL and look at the area under the curve, find K values using integration and stuff like that. So we actually do come back to probability in grade 12 if you can continue on in HL. Okay. And then the next definition, expected value of a random variable. So, it kind of makes sense, and the word expected means what you think will be the result of doing a probability experiment for a certain number of trials. Okay. To be more specific, there are some experiments called binomial experiments. So remember, a binomial is 2 terms. Okay. With a binomial experiment, it means there's 2 outcomes for a trial. So it can be the probability of getting a goal or not getting a goal. Either playing hockey or soccer or whatever. It can be the probability of tossing 6 for a dice or not tossing a 6. That's a binomial experiment where there's just 2. It happens or it doesn't happen. Okay? So, So here, a die is to be rolled 120 times. On how many occasions would you expect the result to be a 6? So we're trying to expectation. Well, what's the probability of rolling a 6? Good? 1/6. Okay, probability of rolling a 5 is also 1/6. So it has nothing to do with what's on there. It has to do with how many sides on a die. Right? There's 6 sides. So the expected value, we use E, although we haven't talked about it yet. To roll a 6 would be 120 times 1/6. So you expect it to happen 20 times. Now, if we actually did that experiment, we talked about this last week, maybe it would happen 15 times for me, 22 times for one of you, 23 times for someone else, 20 times for someone else. But if we kept doing that experiment, our class, other classes, etc., so the number of times we did it approaches infinity, then the number of times out of 120 would happen would be 20. Okay. Another one, each time a soccer player kicks for a goal, she has a 75% chance of being successful. If in a particular game she has 12 kicks for a goal, how many do you expect? Same thing. So probability of a goal, expected value of goal. Would be 75% as a decimal multiplied by 12. Right, that's 3/4 of her kicks are going to be goals. That would be 9 goals. Again, some games you might get 8, some she might get 10, but overall, on average, she's going to get 9 goals for every 12 that she kicks. Probability of a light bulb, that should be a bulb, being defective is 0.03. There's 120 light bulbs in a case. What is the mean number of defective? So expected value of defective will be the probability of being defective times 120 bulbs. So use the decimal, so it's got 3.6, somewhere between 3 and 4 bulbs. So in general, if the probability of an event is P, then the expected number of occurrences for n trials will be n times P. Or P times n, doesn't matter. So if a binomial experiment is repeated n times, and a particular outcome has a probability P of occurring each time, then sometimes we call this the expectation, but sometimes we call it the mean, right? It's on average how many times it will occur out of 120 or out of 12 kicks, okay? So we use E of X, or sometimes we use mu. Mu stands for mu, okay? So mean and expectation, in this case, mean the same thing. So here's another game. So in a game of chance, the player spins a round spinner labeled 1, 2, 3, and 4, and wins the amount of money shown in the table, depending on which number comes up. Okay, so if they spin a 1, they get $6. If they spin a 4, they get nothing. Okay, so assuming the likelihood of spinning a 1, 2, 3, or 4 are all equal. So if you have a spinner, like on a board game, cut into 4 parts, and all the parts are equal. Now, if you play a game, like maybe, I don't know, Sandy's coming, and you know how they have what do you call it, the arcade part or the games part, some of those are really hard to win, right? And they might have something where you have to either throw a dart or something like that, and they might actually change it so it looks like it's equally likely, but they might make this a little bit smaller if that's like the most amount of money you can make. So they might try to trick you a little bit because in a way you're kind of gambling your money and they want to make you money, right? So in any case, in this case, they're all equal, all right? So if there's 4 parts, the probability of, so I'm just going to put it up here, probability of spinning a 1 would be 1/4, 1/4, 1/4, 1/4. Okay. So determine the average winnings on a single spin. This is called the expected value of the winnings. So you basically, you want to get the average that you would get. So if you had a probability of 1/4 for spinning the number 1, you take 1/4 of $6. Okay, so then you add 1/4 of $2. Then you add $3. Then you add 1/4 of $1, and you add 1/4 of $0. Okay, so when there's more than one, you're taking on average what you would win. So 1/4 of 6. Now this is money, so you could use decimals. So that's going to be 1.5 plus 0.75 plus 0.25 plus 0. And that's going to be $2. If you skip ahead a little bit, you'll see the formula for it. So the sum of each random variable times its probability. Okay, we'll give you the expected value. So part B says if the game costs $3 to play, is it a good game to play? Yeah, so that's what gambling is all about. So it's not really, because on average, you're going to lose 50 cents, right? So on average, you lose 50 cents. Okay. Now, you might play the first time, you're going to just go for it, $3, and you might get $6 right away. Okay? Stop. Right? You made money, stop. I listen to my husband sometimes. Go to Las Vegas. Stop while you're ahead. Because on average, the house always wins. Exactly. So don't waste your money. It's fun to do it a little bit when you're old enough to do that. But like I buy lottery tickets, and when we talk about the odds of winning, it's like terrible. It's terrible. So in that 30, we talk about the number of ways of, the number of possible, for example, 649, 6 numbers combinations you can get out of 49. And you're trying to get one of those combinations. And it's like, it's so close to 0. But what keeps us in some of us is that it's not 0. So there is still a tiny little chance. But in any case, be smart. Maybe play, like, you can hear the commercials. What does it say? Something about play what you basically have a budget. So you're good with spending $10, then play a couple of games, and then you've done it if you've lost everything, all of it. Okay? So, as I said, there's the formula. Shows E of X or mu. And often it shows the capital notation on your IB data booklet. So when you get to SL 31 or HL 35 and write your IB exams, you'll get a data booklet. So 2 pages long, and it will have that formula in there for you. Okay. Last one, again, based on data that's been collected, they said, and this probably happens less and less. We made this question up a number of years ago, but you will see at the grocery store, at the checkout, there's magazines there, right? So they put them there because it's kind of one of those frivolous things to buy, and they hope that, oh, you're at the checkout, yeah, last minute, I'm going to buy a magazine. In any case, guys, determine the probability of, so in real life, this is probably much higher now, especially now that most people look at magazines or similar things online. Not, I still like magazines, but I'm older, right? But in any case, buying 0 is a probability of 0.1, buying 1 magazine, 0.23. This is pretty unlikely, but it's also got the smallest probability. So is it a probability distribution? So add these up. Oops. So let's do it at 0.33, 0.41, 0.61, 0.62, 0.82, 0.85, 0.95, plus 0.2. It works. Okay. Okay, determine the mean number of magazines a customer will buy from the store to the nearest 100. So, okay. So that's going to be 0. Just get a calculator. So 0.23 plus. Probably the same thing here. Two times 0.28 plus 3 times 0.21 plus 4 times 0.13 plus 5 times 0.05. Enter. Okay. So basically, a little more than 2 magazines. I'll round it to the nearest magazine, part of the magazine. Okay, but that's expected value. So that's where we'll end for today. Practice there for you.